Good morning all. We move on to the next topic in operating system, which is nothing but the various classical problems of synchronization. So what all problems you get when you go for synchronization thing here. So we'll deal with bounded buffer problem, readers and writers problems, and dining philosophers problem. Coming to bounded buffer problem we even call it as a producer and a consumer problem, where the main thing here is you have two processes, one is your producer process, the other is your consumer process, and we have another shared variable which is nothing but a buffer. You will be having a buffer here. The main responsibility of your producer process is to dump the elements into the buffer, and the job of your consumer is it has to read or take out the elements from that particular buffer. And based on this buffer can be a fixed size buffer or it can be a variable size buffer. But as it implies here, it is bounded, means we only go for fixed size buffer where the size of the buffer is limited here. Now for this to implement, so when a producer is producing an item or inserting an item into the buffer, at the same time you cannot ask a consumer to take out the element. So simultaneous actions cannot be done. So to overcome that particular problem here, we go for using three variables. One is your full, we have three semaphore variables. One is full, which indicates that whether the buffer is full or not, and the initial value of it is 0, and empty where it is related to the size of your buffer, and you have a mutex buffer which will tell whether you can enter into that critical section or not. Now this is the code which we generally use for enabling that particular synchronization. So this is related to your producer problem and this is related to your consumer. As we have seen the variables, full initial value is equal to 0, empty initial value is equal to the size of your buffer. Assume the size of the buffer here I am taking it as 5, and the mutex value for entering into the critical section, you all know that the initial value of it should be 1. Now coming here, assume the producer wants to insert an element or produce an element to the buffer. So we go for weight of empty. So what is your weight value? What will a weight operation does actually just decrements the variable. So what is the value here? 4, indicating that initially you had 5 empty locations. As the producer wants to produce an item here, the empty value will come down. So these are your 5 empty locations. Now your empty value will become 4. Then to acquire a lakh, it goes for weight of mutex. So what is your initial value of mutex? So empty is becoming 4 and this is becoming 0. Now the producer can enter into your critical section and it goes for inserting an element. So it inserts an element, and once the operation is done, it goes for signal of mutex, where your mutex will become your original value as 1, and signal of full. What is your signal full value initially you have taken? Now this becomes 1, indicating that one of the location is been filled. Now the point here is when the producer is inserting an element, you need to take care that the consumer will not interfere. So when the producer is producing an element, what is your mutex value when it is in the critical section? It is 0 and your empty value is 4. Now we will see whether now what is your initial value, since it has not completed, it is equal to 0. Now we will see whether the consumer will be able to enter. Weight of full, since it has not done, it is still in the critical section. Weight of full, it indicates that weight of 0 means the value will be decremented by 1, it becomes -1, and the condition is less than or equal to 0, which will make your consumer process to wait. So when the producer is in the critical section, at any point of time the consumer cannot enter into critical section. Now we move on to the second problem, which is nothing but your reader and writer problem. So here we have two processes, one is your reader process, the other is your writer process. Same as your producer consumer, but here we will go for using a shared variable which is nothing but a file, or you take any of the database. Now when you coming to your reader, any number of readers, so this database is nothing but your shared data which you are using. So any number of readers, when a reader, these readers are there, other reader can also enter into the critical section, but a writer cannot enter into the critical section. Coming to the other way, a writer is in the database, so you will not allow a reader to enter into the critical section or any other writer to also enter into the critical section. So basically we have 4 operations by 2 different processes, P1 and P2, RR, RW, WR and WW. So here RR operation can be performed because both readers can read the file, they will not modify. But when one reader is reading the data, the other reader or writer cannot write the data. The one process is writing the data, the other process cannot read, and two of the process cannot simultaneously write. Now, for this to implement in the form of a critical section, we go for using two semaphore values. One is your mutex, the other is your WRT, where the write variable is initially 1, the mutex is also 1, and since you have not read, it is nothing but your read count. This indicates the number of readers that are currently using that particular resource. Now, this is a code for your writer and this is code for your reader. Now, we will see, now you have a reader process. So, weight of mutex, what is your initial value of mutex? Mutex is equal to 1, WRT is also equal to 1 and read count is equal to 0 because we have not yet started. Weight of mutex, so this will be executed by reader 1, so the value here will become 0. Read count, which was initially 0, will become now 1, and read count is equal to 1, yes. So here you are making weight of WRT, where your WRT will become 0. And next you are coming here, you are making signal of mutex value. Since you are making it as 0 initially, now it becomes 1. Now R1 is already in the critical section, now R2 wants to enter into critical section. So if you just execute the code once again, weight of mutex, what is your mutex value here? 1, so it will again become 0. Read count, so read count which was previously 1 now will be updated to 2. Is read count is equal to 2? No. Signal of mutex, so you again make your mutex value is equal to 1 and R2 will also enter into your critical section. So here R1 and R2 both are in your critical section. Now we will check the other condition where a writer is in the critical section W1. So we will take the initial value of WRT is equal to 1. Weight of WRT, so this will become 0 and it is performing a write operation. So now W2 also wants to enter into critical section. Now when you see the case, when again execute weight of WRT by your second process, since it is already 0, when I decrement it, it becomes 0 and it has to wait, right? So the second writer will not be allowed to enter into the critical section. Similarly, when you cross check, RW will also be not possible. Similarly, WR will also be not possible because both of them, when I am reading, I will not allow somebody to modify the data. Now we go on to the third problem, which is nothing but your dining philosophers problem. And now basically here dining philosophers problem, as it implies, it is nothing but you have the philosophers, and the main job of your philosophers or the activities done by the philosophers is they have to just eat and they have to think. Those are the two jobs. And if a philosopher wants to eat, he has to first of all grab the two chopsticks and then continue with the eating. Now for example, if this philosopher, P5 philosophers has grabbed both the left and right chopstick and started eating, P1 cannot go for eating at the same time. So this is also a problem of your critical section. So now we will see how the solution can be given to this dining philosophers problem. Here we go for using a variable of a semaphore which is nothing but chopstick of 5. So initially why we have taken it as 5, because I am assuming a solution for 5 philosophers. So 5 philosophers are available and they just want to go for eating or thinking, and all of them will be just initialized to 1. Now coming here, now for example if I go for P1 philosophers, first he goes for picking up chopstick of 1, so he goes for chopstick of 1 of I. So I is nothing but 1 here. So when I performing a weight operation, which was initial value of this chopstick was 1, now it becomes 0. Now when P1 philosopher wants to eat, he will first take up the chopstick of I which is on the left side, and he again goes for taking a chopstick on the right side. So chopstick of 1, the value will become 0. Similarly chopstick of I plus 1, which is nothing but 1 plus 1, which is nothing but 2. 2 percentile 5 will nothing but be 2. So P1 philosophers will take the chopstick 1 and he will also take the chopstick 2 and starts eating. Now here the problem is when adjacent philosopher or the neighbor philosopher wants to eat, what are the chopstick he has to grab? He has to grab this chopstick of this and another chopstick. So he has to get a chopstick of 1 as well as chopstick of 2, which is not possible here. So by using this particular solution, Remember, always weight will decrement the value and signal will increment the value. So in this particular case, you are making sure that the adjacent neighbors or the adjacent philosophers will not start eating at the same time. But the main problem in this particular thing is dynamic philosophers problem. If all the philosophers are hungry at the same time, so what will happen? P5 will grab 5 stop stick, P1 will take the 1 stop stick, P2 will take 1 stop stick, P3 will take 3 and P4 will take 4. So each of them are having a chopstick on the left side and each of them are in turn waiting for the other chopstick to get, but none of them will be releasing. So this particular situation will lead to deadlock. The solution whatever we have provided, it only helps you to take that adjacent philosophers are not having their eating part at the same time, but you get a deadlock. So to overcome that particular problem, what we do is we take care that at most 4 philosophers are sitting. So all of them will not make all the file, will make 4 philosophers to be sitting simultaneously. So in that case, one philosopher will get an option of getting 2 chopsticks. So he can have his lunch or eating part and then keep up the chopstick, then the next philosophers can continue. You may get a problem of starvation. Why? Because one remaining philosophers will be waiting for this particular philosophers, but you will not get any problem of your deadlock. This is one way of overcoming it. Or otherwise, you say that a philosopher should start eating only when the 2 chopsticks are available. In the previous solution, we have seen that he is grabbing one and waiting for the other. But here we see that you perform the operation in such a way that he is able to get 2 chopsticks at the same time. And the other one is we go up giving an order. So when you go for odd philosophers, he picks up the left and then the right chopstick. But when you go for your even philosophers, even is P2, P4 philosophers, he first picks up the right chopstick and then goes for the left chopsticks. So these are the different classical problems of synchronization and the methods how to overcome that.